Now we have a nitrous oxide. And so, in reality, an oxime is going to exist as both this and this in equilibrium. We call this a tautomer. Tautomer, and we'll talk about tautomers more in the next few chapters, but a tautomer is, they're isomers of something where a bond with the same primary structure, just the bonds change a little bit. So you can think of tautomers to be very related to resonance structures, except a proton moves too. So imagine if you draw a resonance structure, where now you have a minus charge somewhere and a positive charge with the proton somewhere else, and then the minus charge in the resonance structure acts as a base and takes that proton. That gives you something that's no longer a resonance structure because you broke the bond. But what that does is that gives you a tautomer. And this is an example of a tautomer of this. So tautomers aren't resonance structures, but they're equilibrium structures, meaning the two tautomers are always being in equilibrium with each other. But you can really think of them as being more related to resonance structures than a typical equilibrium would be. So we'll talk about those more in chapter 18. I just wanted to introduce that now. But just the thought that an oxime, because you have these two pairs of electrons, can exist as an equilibrium between these two things. And you can get to the other tautomer by drawing the resonance structure and then quenching the charges with a proton transfer. This will be really big in chapter 18. Yes?
What's on the third one at the top? What is that?
Right here?
Yeah, the N.
This right here?
Yeah.
That's nitrogen.
What's the middle substance?
The middle...
So there's an OH and an H and then the middle.
Yeah, there's an OH and an H. There's an NH2OH because we had NH2OH added to here. Does that answer it?
Yeah.
So now, what about but instead of using a nitrogen bound to a hydrogen an oxygen, what if you use a nitrogen bound to a another nitrogen? Will this give us an oxime-like thing, but with a nitrogen? Will the mechanism change? Going from here to here, will the mechanism change? Absolutely not. It's just we're replacing the OH in this case with an NH2 in this case, where everything's the same. Again, this class is just a variation on itself. Everything's a variation and something we've already talked about. So indeed, in this case, we will come up with something like this. After all our proton transfers, we will come up with this. Again, so just forming the amine, like the mechanism we've gone over 2 or 3 times today and 1 or 2 times on Friday. So we'll go over this mechanism again. We get this, and then we have the tautomerization. But, what's up? Then once we form this amine, we can once again do the tautomerization. That gives us this. Okay? And so, let's compare the oxime tautomer, or at least resonance structure towards the tautomer with this resonance structure. Which one of these resonance structures do you think is stable? Well, let me draw a dotted line so that you guys can have some separation. So, what do you think is more stable? This resonance structure that leads to this tautomer, or this resonance structure? This one or this one? Let's compare the 2 resonance structures between the 2 different reactions.
Look the same.
Well, let's compare. This has an oxygen with a positive charge. This has a nitrogen with a positive charge. I said to people, high five. Why?
Because the nitrogen is less electronegative. So
Boom! Exactly. Yes, that was a good high five. Exactly. So what that means is this resonance structure is more stable than this resonance structure. So this is going to be a more prevalent contributor to this case than this is to this case. And so what that means is this is real. And then we actually can form a fair bit of this grabbing this proton. To give us this. And so with hydrazines, we can form a fair bit of this tautomer, and the equilibrium is going to favor, especially if you heat it up, this tautomer. By the way, this stuff I just showed you, forming this amine and then forming this tautomer, guess what I'm teaching you right now? The Wolff-Kishner mechanism. So let's keep this in mind, and let me draw up the Wolff-Kishner transformations for you, and let's finish up the mechanism. So remember, when I talked about the Wolff-Kishner, it was you take a carbonyl, and you take hydrazine, how easy do you think it is to get hydrazine in this country? It's easy. You can buy it. How easy do you think it is to get hydrazine in other countries? Nearly impossible. What is hydrazine also known as? Rocket fuel. We actually got the speaker on Friday from UCSD. He's done a lot of hydrazine chemistry. Really cool hydrazine chemistry that applies to this really specific Diels-Alder that he uses to do Diels-Alder in living things. So this guy's making chemical probes that does Diels-Alders in like living cells and animals to ask scientific questions. That's probably the coolest application of the Diels-Alder reaction I've ever seen. But in order to make his dienophiles, he has to use hydrazine. And so he was saying, oh, he had this great paper showing all this really cool stuff you can do. And then he started getting emails from people outside of this country asking him, is there anything we can use besides hydrazine? We can't get our hands on it. Because we're not in the country that we allow, as in the United States, allow to get their hands on rocket fuel. I heard that at dinner and I like that. So anyway, you take hydrazine, KOH, and heat. And the product you get is replacing the carbonyl with two hydrogens. And I can tell you that this mechanism goes through something very similar to this. And I'm going to show it to you. And then we'll see a nice application of this amine-iminium stuff. So, basic conditions and heat. Are we going to need acid to add into this with heat? No, with heat, we can get away with adding into here. Okay, so we get this. And now this water, and obviously take this proton. Is this going to be a favored equilibrium? Yeah, in this case it is, because this has a pKa of like 16, this has a pKa of 10, so absolutely. In this case, because it's an O minus, not an O neutral, it can definitely take this proton and be favored equilibrium-wise. Okay, next question. Usually in these mechanisms we talk about we have some kind of water or acid protonate this so we can kick off H2O. Under KOH conditions, so strong base, will we protonate this? Absolutely not, right? We're under basic conditions, so if we protonate this, it wouldn't last very long. So that's not going to happen. But we're under basic conditions with tons of OH minus, and we're heated. Do you think the lone pair of electrons under these heat and basic conditions can kick off OH minus? Under heat and basic conditions where there's a ton of OH floating around, do you think it's reasonable to kick off OH minus? Sure, basic conditions. Again, we're heating it. And by heating it, I mean a big triangle, not a small triangle, a big triangle. So yes, we can absolutely, and I'll outline it in red, absolutely kick this off. They give us this, and of course we kicked off OH minus. So under basic conditions, is this proton going to stay around long in the nitrogen?
Negative.
Absolutely not, right? This proton is going to be deprotonated pretty quickly. And so I would love to do magic board chemistry and erase it, but I won't. So the base formed, or the base reactions go quickly grab this. To give us this. So now we just formed this, and so now we can do the equilibrium. So let's first draw the resonance structure. Let me make the arrow a little bit smaller so I have room to draw it. So this is these electrons kicking in to this form a nitrogen-nitrogen double bond, and then those electrons kicking in to give us a carbon minus charge. So this would be a resonance structure. And now we can complete the tautomerization by having the minus charge in carbon grab the proton and the positively charged nitrogen. I'm going to try to get this in order if I can not drop my pen. All right, so this is what we've done so far. So that gives us this. So through this, we put on our first proton, right? We're replacing the carbonyl with 2 hydrogens, and so now we've already put on our first hydrogen. So we're halfway there. And in theory, we're actually much more than halfway there. So we have a nitrogen-nitrogen double bond. Does this make you think of anything that could form fairly easily that's really stable? Nitrogen gas, right? And eluting nitrogen gas is one of the most powerful thermodynamic forces known. Why is giving up nitrogen gas one of the most powerful thermodynamic forces known? Yeah, it's a stable product, but it bubbles away too, right? Once you form nitrogen gas, it's just going to bubble away in the atmosphere. And then that brings our good friend Mr. Le Chatelier into play. We're removing one of these products from the equilibrium, so that's going to shift the equilibrium all the way to the product because nitrogen's bubbling away. So the second we form it, it's going to bubble away, and then Le Chatelier is going to take control and push the reaction to completion. So then what happens, and this is something that in theory, if you don't think of Le Chatelier's theory, it looks horrible, right? We have base first grabbing this proton. I'm going to draw this way too stepways to prove a point, but in reality, you can draw this fairly concerted if you'd like. So to give us this, And first off, do we really like this? We go from OH minus pKa of its conjugate acid being 16 to a nitrogen anion, right? And nitrogen is less electronegative, so it's not going to like the anion as much. So pKa-wise, this probably isn't the most favorite thing, admit it. And then the next thing we're going to draw is that these lone pair of electrons are going to kick down to give us, let me redraw the product with a little more space. So then these lone pair of electrons are going to kick here, causing these electrons to go down to give us our secondary carbanion plus N2 gas. So that's not very nice, right? We went from a pKa of 16 to a pKa of 50. This happens though because we're giving up nitrogen gas. And nitrogen gas is a powerful primary. But is this going to sit around very long? We're in basic water. So yes, there's tons of base, but there's also tons of water. So then some H2O in a solution is just going to quickly be deprotonated by this anion to give us our product. Longest mechanism of the class, right? Would you call this the hardest mechanism of the class, though? You know, we'll just break it down, right? First step is just an acetal to amine formation. We've talked about that several times. Then it's a tautomerization, proton transfer. They give us this. And then it's base grabbing a proton, being driven by Le Chatelier's theorem and the formation of N2 gas, causing it to go all the way up here, and then giving us our CH2 instead of our C double bond oxygen, so carbonyl to a methylene. A useful transformation. My next question. Previously in this class, the way we did this was doing an LAH reduction of the carbonyl to get the alcohol, PBr3 to go alcohol to bromide, and then LAH to go bromide to hydrogen. Is this easier? It is. So in all reality, if you want to go carbonyl, C double bond oxygen to CH2, so when I reduce the carbonyl to the CH2, this is probably the best way to do it. By hydrazine rocket fuel, luckily we only get out of the USA so we can access it. We can buy it from Aldrich. And heat and KOH. And we do this amine chemistry, condensation to give the iminium, then from the amine, tautomerization, nitrogen gas flying off, gives us our product. A lot. But this is pretty much the pinnacle of the mechanism for amine chemistry. So now we're pretty much done with amine chemistry. And so now the final thing to talk about, in the last 5 minutes, I'm going to introduce this reaction. So, if you haven't noticed, what's the theme of chapter 16? What? Oh, well, is this the heights? Yes.
I had one question about in the middle of the board where the lone pairs and the nitrogen are going down and the OH is being kicked out.
Yeah.
So you say because of
this case right here.
That case, yeah, because the solution contains
Base, yeah.
So it helps it move out. And
Exactly.
How does that happen?
Well, so first up, we're heated, right?
Okay.
And this every step in this every step in this reaction is equilibrium, right? And the less, so yeah, that might not necessarily be the best thing in the world, but we're heated and we're giving up N2 gas. So pretty much these equilibriums could totally be unfavorable, but because the less steps giving up N2, which is going to be a super favorable equilibrium, that can push the reaction forward. And so as far as water, is this kicking up OH to give us this, or water adding into this to give us this, right? That's a real equilibrium. We're going to have some kind of mixture of that. But the thing that's going to drive the reaction is Le Chatelier's theorem and the fact we're giving up N2 gas. But in general, as a rule of thumb, under basic conditions, it is okay to kick off OH minus. You'll need some heat, and we'll be talking about this in chapter 18 and beyond. But under basic conditions, it is not unheard of to kick up OH minus because you're in a slew of OH minus to begin with. So what's adding one extra molecule to the sea of OH minus going to really do the stability? Under acidic conditions, don't dream of it. Acidic conditions, just fluorinate it and kick up H2O+. But under basic conditions, we can kick up OH-, especially when there's heat. So just let me hint at the last major reaction of chapter 16, which we'll go over partly tomorrow. So the theme of chapter 16 is nucleophiles adding into carbonyls, namely ketones or aldehydes. And so first we started out nucleophiles like H-, diol, stuff like that, that's going to add and give us alcohols. Things that will be stable products. Then we talk about acetals, so adding water or methanol into a carbonyl to give us our acetal or ketone. Those things they're stable under the right conditions, but they're also unstable under other conditions. But you know, by and large, we can think of them as fairly stable organic molecules. Then we talk about oximes and hydrazines adding into carbonyls. And those give unstable products that do chemistry, like the Wolff-Kishner we just talked about. And then the final reaction we're really going to talk about in chapter 16 before we move on to chapter 17 is called the Wittig reaction. So just get your minds percolating around this. What a Wittig reaction is you take a phosphine attached to an alkyl group. So phosphines are neutral when they have 3 substitutions attached to them. They're positively charged when they have 4 substitutions. So since these hydrogens on this carbon adjacent to phosphorus are adjacent to a cationic phosphorus, do you think they're going to be acidic?
Yeah.
Absolutely. This is very similar to the Swern oxidation sulfonium case. So you can take a fairly weak base and form what we call an ylid. So an ylid is because we're talking about a Wittig. An ylid is a molecule that has both a positive and minus charge. And so when the positive and minus charge are next to each other, they can actually exist in equilibrium with the double bond replacing the 2 charges. So the minus charge going into the positive charge. But reactivity-wise, if you see anything that looks like this, realize it's going to really behave like this.
Is that equilibrium or a
You're right. Good call. Good call. I get all worked out with the Wolff-Kishner and all the equilibrium part. I wasn't paying attention. So we've got this. It's going to act like this. And so what happens, if you take a nucleophile, and for the Wittig, an electrophile, for Wittig, the electrophile is going to be an aldehyde. So in this case, I'm just going to draw formaldehyde. What's going to happen, of course, is this minus charge is going to attack the aldehyde. And what that will give us, and I'm going to outline the aldehyde in green so we can tell